So, moving into chapter 4 today, specifically the chain rule, which is the next rule in taking derivatives. So, consider, for example, the function f of x is equal to the quantity 4x cubed plus 1 squared, which if you distributed that, it would be 16x to the 6th plus 8x cubed plus 1. So far, no problem, right? We can take the derivative of that really easily. It's 96x to the 5th plus 24x squared. Okay? Now, what if we didn't want to multiply it out first? What if instead we're like, well, isn't this a power? Can I not use the power rule? And the answer is no, you can't use the power rule and to be finished. You have to use the power rule plus something. Okay? So if we just did the power rule on this, notice I'm not writing f prime is equal to because it's not. We would get 2 times 4x cubed plus 1, which would be 8x cubed plus 2. And you're like, okay, well, how far off am I? Well, it turns out 8x cubed into 96x to the 5th is 12x squared. And 2 divided into 24x squared is also 12x squared. And you're like, that's an interesting coincidence. Where in this expression could we get 12x squared? So if you're looking at this expression, how could we get 12x squared from that?
Derivative of 4x cubed plus 1.
Yeah, it's the derivative of 4x cubed plus 1. The derivative with respect to x of 4x cubed plus 1 is equal to 12x squared. And this is the idea behind the chain rule. We could take this and multiply it by 12x squared and get the correct derivative without having to multiply the original out. Now, if it's just squared, it's no big deal to just do this. But what if this had been to the 7th power? Right? That's pretty ugly. But I could use the power rule and then just multiply it by the 12x squared. This is the chain rule. It says that if f is differentiable at g of x and g is differentiable at x, then f of g of x is differentiable and the derivative of f of g of x is f prime of g of x times g prime of x. So basically what you're doing is you take the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. Okay, it's a little bit like, and it's not a great metaphor, but it kind of works, I think. Imagine that you are eating an M&M, except you decide not to chew it. You decide to just put it in your mouth and let it dissolve. What will happen first?
Sweet.
What?
Put it outside with it's a sugar outside, right? It's the
Right, so what would happen?
Get it melt.
What melts first?
The outside.
The outside coating melts, leaving the inside alone for a moment, right? The inside's unaffected until the outside is gone. And then the inside would melt. Same thing here. We take the derivative of the outer part, leaving the inside part alone, times the derivative of the inside part. That's the idea behind the chain rule. And if you had a function inside a function inside a function, it's okay. It's okay. I always think there's a parade going by or there's an elephant out there or something.
Yeah.
Oh,
Earlier today, there was a squirrel in the gutter, and my entire geometry class is like, "Look, squirrel!" And I'm like, "Have you never seen squirrels before?" If you had a function inside another function, well, then that's a peanut M&M, right?
Yes.
The outside part, leaving the two inside parts, then the next part, leaving just the peanut, and then the peanut. So and some people equate it to peeling an onion one layer at a time. You do the outside layer, leaving the next layer alone. Then you do the next layer, leaving the next layer alone, et cetera, et cetera. So in Leibniz notation, if y equals f of u and u equals g of x, then dy dx is dy du, the derivative of f with respect to u, times du dx, the derivative of u with respect to x. I kind of like this notation because you can think about it like the du's cancel and it's dy dx. Okay? So the derivative of a composite function is the derivative of the outer function with the inner function left alone times the derivative of the inside function. All right, so that'll allow us to do things like this equation, which we could not do previously. The other example that we had at the beginning, we could square it and then take the derivative term by term. But with this, we had no way of doing this function. So the derivative for this function, dy dx, is going to be, pardon?
Right. Y and the small
Y prime.
Yes.
Learn the words. Okay,
Y point.
y prime. Yes, but you need to know both.
Yes.
Okay? So I'm going to start by taking the derivative of the outside piece. What's the derivative of sine?
Cosine.
Cosine. And the inside function will remain the same. Times, now I'll multiply that times the derivative of the inner function, which will be 6x plus 5. And that's it. Pardon?
You have to multiply it.
Well, remember that the 6x plus 5 is not being multiplied times this, it's being multiplied times all of it. So if there's any adjusting at all, it's almost always writing this first, because sometimes people do confuse it. It's like, am I taking the cosine of all of this? No, I'm only taking the cosine of this part. So to make it clearer, a lot of times you'll see it rewritten like this: 6x plus 5 times cosine of 3x squared plus 5x. So that there's no confusion as to what the argument of cosine is. When I say argument, are you familiar with that? Okay. All right. Page 2. So an object moves along the x-axis so that any time t greater than or equal to 0, its position is given by x of t is equal to cosine of t squared plus 1. Find the velocity of the object as a function of t. All right, well, velocity, how do I find that? Derivative of what?
Position.
Of the position function. So it would be x prime of t. So this will be negative sine of, leave the inside part alone for now, t squared plus 1, times, now we're ready for the next layer, 2t. And again, we will typically rewrite that as negative 2t sine of t squared plus 1. Now, occasionally you have more than two functions. That's what I was talking about earlier. You can have 3, 4, 5. Now, in practice, we almost never get past 3. Okay, it just gets kind of silly after a while. But this one, it actually is a function inside a function inside a function. But it's not offset with parentheses, is it? I think it's really helpful when you have one of these, to take the time to rewrite it so that you have each layer separated by a set of parentheses, so that you see that there are actually 3 layers to this. Otherwise, it's really easy to miss it, especially on one like this where it's sine of 3t. It's easy to go, yeah, sine of 3t, the derivative is cosine 3t. Not quite. Okay? So then g prime of t, the derivative of tangent of something is?
Secant squared.
Yeah, secant squared of that something. So secant squared of 5 minus sine of 3t times the derivative of 5 minus sine of 3t. So I have to use the chain rule again. So the derivative will be negative cosine of 3t times the derivative of 3t, which is 3. Typically what we'll do on one like this is take any constants that we can factor out, put them all together at the beginning of the expression. So this would be negative 3 secant squared of 5 minus sine 3t times cosine 3t. Might it have been better to put the cosine before the secant squared? Perhaps. It's not actually important to this. You just may see it rearranged like that, especially on multiple choice questions. Okay, any questions about that so far? It's not too bad. So slopes of parameterized curves. So a parameterized curve, x of t, y of t, is differentiable if both x of t and y of t are differentiable, and x prime of t is not equal to 0. So here what we're doing is we're doing parametric equations so that we can have motion in the x direction and in the y direction simultaneously instead of just motion along a line. This, by the way, is one of the differences between AB and BC. AB doesn't do parametric equations at all. BC does. Okay? So by the chain rule in Leibniz notation, dy dt would be dy dx times dx dt. So then solving this for dy dx, we get dy dx is dy dt over dx dt, which actually kind of makes sense. The change in y with respect to x is the change in y with respect to t divided by the change in x with respect to t. So let's do an example of that. So if we want to write an equation for the line tangent to x equals secant t, y equals tangent t, for t between negative pi over 2 and pi over 2 at t equals pi over 4. All kinds of good stuff going on here. So in order to write the equation for the tangent line, we need to know 2 things. We need to know a point, and we need to know a slope. So for the point, we'll just substitute in. So x is going to be equal to secant at pi over 4. Remember that secant is the reciprocal of cosine. Cosine at pi over 4 is square root of 2 over 2. Flip that over, that's 2 over the square root of 2, which is the square root of 2. Y is going to be equal to tangent at pi over 4, and that's one that everybody ought to know really quickly. 1. Because sine and cosine are the same at pi over 4. So we've got our point. Our point will be square root of 2 comma 1. Well, now we've got to find the slope. Well, dy dx, which will be the slope, is going to be dy dt divided by dx dt. So the derivative of tangent is secant squared, and the derivative of secant is secant tangent. So it's secant. Be sure you put the arguments. I think it was this class. Somebody was leaving off their arguments on things. It's important that you have, tangent of what? Notice here on this that I can factor out one of the secants. So this will be secant of t over the tangent of t. So then the slope of the tangent would be equal to secant at pi over 4 over tangent at pi over 4, both of which we've already calculated, because secant at pi over 4 was the square root of 2 and tangent at pi over 4 was 1, so this is the square root of 2. That was nice. That made this a little easier. So my equation for the tangent line would be y is equal to 1 plus the square root of 2 times x minus the square root of 2. Again, your book and probably any free response question would likely change this into slope-intercept form, which would be y is equal to the square root of 2 times x minus 1, because the square root of 2 times the square root of 2 would be 2, so it would be negative 2 plus 1. Okay, I want to, real quickly, show you what this looks like. It's kind of cool. Doinked, doinked. Yes, I really do want that. I'll move it to somewhere where you can see a little better in just a second. So, and I have to remember how to do this every year. I'm like, what? So x, was it x is equal to secant t?
Yes.
I can never remember the specifics of how you have to do it. Y is equal to tangent of t. And let's see if it'll do it. Yeah, because of a bad operator. Bad operator. Requires that you specify a domain. Okay, I'm getting closer. I can never remember if they accept square parentheses or not. The problem that's going to be on this one is that at negative pi over 2 and at pi over 2, tangent's not defined. So it will fuss at me if I try to put in actually what negative pi over 2 is. So I'm going to do a little cheat thing. I'm going to do negative pi divided by 2 plus 0.001. Really close to it. Comma. Pi divided by 2 minus 0.001. Now I get to find out if it likes those or not. Doesn't like those. Must be these. Ah, there it is. Fairly boring graph. It's kind of a V-shaped U. And then I'm going to go ahead and put in the tangent line, and hopefully this is going to work out. So y equals, on this one, SQR, I believe, is how you do square root. 2 times x minus 1. And look at that. Nice little tangent line there. And it's at the point that we thought it would be. Square root of 2 is about 1.4. It's 1.414 approximately, so a little less than 1.5. That looks about right. And the y coordinate was 1. Oh, so right there. Okay? That is one of the nice things about, I mean, you could do that on your calculator also. It works out just fine. But I wanted you to see that, yeah, it really did work, as opposed to some of the other things I've tried this year where it really didn't work. All right. So let's find the slope of the line tangent to the curve y equals sine to the fifth x at x equals pi over 3. Well, although this is a handy way of writing things, what does sine to the fifth x literally mean? No?
Sine of x to the fifth.
Yeah, and when you say sine of x to the fifth, the problem is it sounds like it's the x to the fifth. It's really sine of x, parentheses, to the fifth. Sound effects optional. Okay? So y is equal to sine of x to the fifth. You said 5 sine x times tangent?
No, I said 5 sine x times together.
Oh, times together.
Yeah.
I have great difficulty understanding you some days. I'm sorry.
You know, my Chinese accent sometimes does influence my.
I understand Lynn just fine.
Yeah.
Oh, yeah,
it's
yeah.
Different language, different. Sometimes can't accurate.
Can the accurate? Sometimes it's the, the words.
Yeah, I just had a bad grammar.
Yes.
Yeah. Oh, okay.
Okay. So then, and because you like y prime, we'll do y prime this time.
Hey, thank you.
You're welcome. So we'll start with the outer function, which is the power function this time. So this will be 5 times, we'll leave the inner function alone until we have completely taken the derivative of the outer function, times the derivative of the inside function. So that'll be cosine x. Now, if you want, you can take the time to write that as 5 sine to the fourth x times cosine x. Yeah, I'm pretty ambivalent on the whole thing. And actually, you probably will get to the place where you can do ones like this without having to write it with the parentheses. You certainly aren't required to, but that's why it works out this way. So then the slope of the tangent at x equals pi over 3 is 5 times the sine at pi over 3. And here I do write it with the parentheses to the fourth times the cosine at pi over 3. And yes, I do expect you to be able to do some unit circle work. Now, if this is a free response question on the AP exam, actually that's sufficient. They will let you leave it that way because they say that that's all numeric. To which I say, bull. It is not all numeric. Sine is not a numeral. Okay? It's an operator.
Yeah, no.
But then again, if it was the square root of 7, I'd be like, yeah, don't try and figure that out. So I'm kind of a hypocrite that way. So this will be equal to 5 times sine at pi over 3. Square root of 3 over 2. Thank you. We want to raise that to the fourth. And cosine at pi over 3 is 1/2. So we're going to have 5 times the square root of 3 raised to the 4th power.
6 or 9. One of those.
It is one of those. It's 9.
Yeah. Second time.
Over 2 to the 4th is 16 times 1/2. So that's 45 30-seconds. A little more than 1. Almost 1.5.
Still not done. Keep circling like the partial answer, and I'm like, oh, we're done. We're not.
All right. Is this the last one? Yeah. So another way, and I don't think I've ever seen it written this way on the AP exam with the FOG for a composition. Have you guys seen that before?
Is that fear of God?
Is it what?
Fear of God.
No,
Oh, okay.
no, it's not fear of God. So F means that.
Why?
It's an older way of writing. It's less writing.
Barely.
Yeah, I don't care for it
Same
personally.
number of letters, just cut a less.
Lots less parentheses. Okay. So what we can do here is take the derivative of the outside part with respect to u times the derivative of u with respect to x. Okay? So f of g prime is going to be equal to, we'll start by taking the derivative of f with respect to u. So that's going to be u minus 5 times 3u squared minus u cubed plus 3 times 1 all over u minus 5 quantity squared times the derivative of u with respect to x. So that'll be 2x plus 3. Now, you can, if you want to, do several different things at this point. I do a little bit of cleaning up for this quotient, and I leave this alone for the time being. Okay? So that's going to be equal to 3u to the third minus 15u squared minus u cubed minus 3. Be sure to distribute the negative sign over u minus 5 quantity squared times the quantity 2x plus 3. Be careful not to lose the parentheses on the 2x plus 3. That's an easy thing to miss. All right, and then let's finish cleaning that up. It's 2u cubed minus 15u squared minus 3 over u minus 5 quantity squared times 2x plus 3. Now, I have had students that at this point would go, okay, well now I'm going to substitute this in for every u and work that out. And I'm like, oh gosh, please don't. We don't need to, because we're interested at x equals 0. So at x equals 0, u is equal to 0 squared plus 3 times 0 plus 5 is 5. So that means that my derivative of this composition is going to be 3 times 5 cubed minus 15 times 5 squared. Oh, sorry, 2. My fault. I accidentally looked up a row. Minus 3 over, oh crap, I forgot about this. This doesn't work out very well at all, but I'll leave it. Every year I'm like, I'm going to fix that for next year. And do I? No. And then here we're going to do 2 times x plus 3. So that's 2 times 0 plus 3. Do you see where the problem is? The denominator of my fraction is 0. That's bad. But we'll pretend like it's not for the moment. So this is going to be 250 minus 25 times 15 is 25, 250 plus another 125 is 375?
Yep.
Thank you. I'm not very good with numbers. Times 3. That's negative 128 times 3 is negative 384. And since it's over 0, it really doesn't matter. It's undefined. We'll assume that I did any other arithmetic right, but it doesn't really matter because it ends up being undefined. Any questions about that? It looks horrible, but it's not all that bad, really. Okay? All right.